All right, so using our periodic table, we've got 7. So the potential set of numbers that could be this principal quantum number are 1, 2, 3, 4, 5, 6, or 7. That corresponds to these rows. So we start to describe the position of an element and its associated electrons based on, first of all, the row that it's in, because that tells us the number of shells. So if we have the nucleus of an atom, and nuclei are always positive because they have protons and neutrons in them. And if we look at the shells, and this is the Bohr model, right? The Bohr model is also called the planetary model, and I'm using these ideas as concentric circles, and this is the idea that we have that the electrons are found in a certain vicinity. We think about the way that they travel in one way, and we think about also the positional area where they might be found in another way. We can think about these as being probability areas. If I could take a point and say, what's the probability of the electron being at any given point in time, that the probabilities are going to match up to these layers around the nuclei. Well, if we look at the layers and the corresponding numbers with Max Planck's theory, the way I've drawn it here, it looks like the concentric layers are all fairly equidistant from each other. Well, Planck's disagreed with that. If we look here at this particular representation of the shells of electrons that surround the nucleus of an atom, we could say that the nucleus of the atom is going to be down here in this area, and this is going to be n equals 1, which corresponds to that first row on the periodic table, or the first area where you might potentially find a set of electrons around the nucleus of an atom. So if we look at that value, it's way down here. That's n equals 1, okay? So energy is in the vertical axis, meaning an electron needs to have a certain amount of energy to exist in an energy shell or in an orbital beyond the nucleus, because the nucleus is positively charged, the electron is negatively charged. They're attracted to each other, and it's the centripetal force that goes around as the electron is moving that it is also alternatively attracted to the nucleus as well as repelled by its motion as it travels around the nucleus. Right? So if we look at this first layer, the first layer is fairly close to the nucleus. So if we look at the second layer here in n equals 2, look at the giant amount of distance between the first and the second layer as compared to the second and the third layer, which then correspondingly decreases third and fourth layer, and so on. So as you go out from the nucleus of an atom, the first layer and the second layer are really far apart from each other. And the second and the third layer, not so much, and so on and so on. And what is that little tiny funny squiggly line, like a figure 8 that fell over, at the top of the energy graph here? What is that? Infinitesimally small. So really the differences between the n equals 6 and n equals 7 are so infinitesimally small because they have such high energy that it's really, really difficult to define the differences between them. So if you're looking at it, you have to have different amounts of energy to occupy these orbitals, and that's what Bohr and Planck agreed on, is this idea of the different energy levels. The amount of energy that's absorbed is related to the wavelength and the frequency. And if you look at the colors of light here, remember the Roy G. Biv thing? Decided that Biv G. Muir was the short wavelengths. These are the long wavelengths. This is the high energy, and this is the low energy. Right? Long wavelengths and short wavelengths. You look at the green. The green represents energy overall, not just the wavelength itself. So the green energy versus the red energy has to do with how the energy is distributed, not necessarily the wavelength of the light. When I was in high school, we did an experiment that was supposed to give us this idea of Schrodinger's idea of the development of where these electrons are. And if you think about, it's a flat surface when we discuss the position of electrons, but really you need to think of it as three-dimensional orientation. We have the x-axis, right? We've got the y-axis, which is vertical, and you have the z-axis, which is coming out at you from the middle. And the way that electrons are distributed is sort of in a ball, not in a flat area, but in a ball that is at the juncture of the three axes. And the density of the electrons gets less and less as you go further least when I was in high school, 30 something years ago. 111, we did in high school chemistry, our teacher says, okay, put a dot in the middle of a piece of paper. I want you to take that piece of paper and you're going to put it on the ground. And then you're going to take your pen and pencil. And you're going to drop that pen and pencil 100 times and try and hit the dot. Okay, so 1, 2, 3, 4. You can imagine that took almost the whole class periods to get the 100 dots that we needed. But when they were done, our dots went along like this. You know, if you're aiming for the middle, the majority of them are going to be around the center. And as you get further and further away from the center, they're going to get less and less dense. You have to think about these. If you've ever had a statistics course, I think if you could plot the statistical probability of an electron being at any given point in time, you could plot it as a dot. And so the dots would look like that and would disperse and be very dense in the nucleus of the atom, and further as you go away, they would get less and less dense. And this whole idea of how this is put together is quantum mechanics. Now, I'm giving you my version of quantum mechanics, how I imagine it in my mind. It may not be the same as what other scientists think of. This is the distilled down version of quantum mechanics, so that's what I like to use. There's some equations that we're not going to go through that you don't need to do for your homework. But the big picture is this quantum number is the orbital. When you talk about an orbital, I've also heard the word shell being used, and it just has to do with that discrete distance of zone of probability that an electron could be at. So you'll hear orbital, or you'll hear shell, or you might hear energy level, depending on who it's talking or what reference that you're reading. And there's 3 quantum numbers we use to describe each of these electrons and their position. The first one is the principal quantum number, which is n, and that's the set of numbers 1, 2, 3, 4, 5, 6, or 7. There's this idea of this angular momentum quantum number. I'm not going to worry about that because that's something that really doesn't make a lot of sense to us and to our comparisons, but I am going to use this idea of the spin, because spin tells us a lot about the structure of an electron. So we have some numbers that we can use, and the spin also corresponds to positions of electrons on the periodic table. If you look at a shadow box outline of the periodic table, we've got S, P, D, and F have to do with the spins on the electron. So they are a particular distance from the nucleus, but they're also traveling in a particular way, and the way that they travel we call the spin. All right. This is an old PowerPoint, so we're not going to use this magnetic quantum number, but we do need to look at the way that s orbitals appear. So one s orbital is a very small concentric spin or area of probability for a s spinning electron. Some electrons in these 2 columns as you're adding across the row. We'll talk about that. 2s, further away from the nucleus. 3s, even further away from the nucleus. But you can see that if you think about them the way they're spinning, they're sort of spinning circular. And some animations I've seen, it shows electrons that are in the same shell and subshell chasing each other as they spin, and that's not how it works. Okay, one electron will go in one direction, the other one goes in the opposite direction. So they don't chase each other, they go in opposite directions from each other, and that actually turns out to influence a lot of the physical properties of the elements, this opposite spin that they do, including magnetism. You know that not all metals are magnetic, right? Y'all know that. Yes? There's certain areas on some of your fringes that you put a magnet on, and other areas that you can't put a magnet on, even though they're all metal. What's a metal that's always magnetic? Iron is one that's always magnetic, and it does have to do with the position on the periodic table. All right, so the s orbitals, if you look at the distance, how they are from the nucleus, the top 3 graphs there show the distance of these s orbitals from the nucleus, and if you could divide up the atom and look at the concentric s orbitals, 1, 2, and 3, you see that the way that the graphs are being shown is they're just showing the amount of electrons in that vicinity as evidence for this idea of these spins or these suborbitals. P spinning electrons, once again, you've still got the 3 axes, the x, y, and z, but now the zone of probabilities look more like a dumbbell shape. Okay? So you have a zone of probability around the x-axis, a zone of probability around the y-axis, and one that's coming out of the z-axis. So you can also have S and P's overlap
overlapping, and we call that hybridization that we'll talk about in the molecular geometry lab today. The d orbitals are even more complex. So s are super simple, p are a little more complex, d are even more complex, and f are so complex that we don't even try and draw pictures of them, which all leads to this idea of electron configurations. Now, electron configurations, go back up here, we're going to use the formula, a different formula than what is in this particular PowerPoint. Let's see here. No, that's not the one I want. There we go. All right. If you're looking at writing electron configurations, and electron configurations show using shorthand method how the electrons in a many electron atom are distributed by orbital or shell, as well as subshell, how it's spinning. And that turns out to be important to us as scientists because that determines a lot of physical and chemical characteristics of the element. All right, I'm going to use these both sort of simultaneously because we're going to refer to the periodic table. So, electron configurations, like I said, is just a shorthand way of showing the distribution of electrons in an element. The basic formula, I like to abbreviate with NXS. N, we're going to call the principal quantum number. Remember, that's the set of numbers 1, 2, 3, 4, 5, 6, or 7 that has to do with the rows on the periodic table. So n equals 1 is hydrogen and helium. N equals 2 is lithium all the way to sodium. N equals 3 is sodium all the way to argon, etc. All right. X has to do with the spin. And that can be the set of values either S, P, D, or F. S are circular, P are the donut shaped, D are more complex, and F are so complex you can't even think about it. S has to do with the number of electrons in that subshell that are spinning in that particular direction. So that's how we go about these electron configurations. So we're going to start with some really simple electron configurations. And I ask for your patience because as we go along, you're going to see patterns and it's going to make more things a little bit more apparent after 2 or 3 examples. All right. So for this, we say we're going to start with something like hydrogen. Hydrogen has a very simple electron configuration, right? It's in the first row, so my N is 1. It's in the S spinning block, right? Here's our block of spins on the periodic table, S, P, D, and F. So it's in the S block, and it has 1 electron in that S spinning block. So hydrogen's electron configuration is pretty darn simple. Let's do something a little more complex. Let's try something like oxygen. Oxygen is over here. Now I have to show all of the electrons in all of the shells of oxygen, not just the ones that are unvalent. So I have to start with everything that I'm beginning with. Now for purposes of electron configuration, I tend to like to put helium over here in my own mind just because it makes easier sense. So if I'm doing oxygen, electron configuration, I have to show as I'm going along, the first row is full, 1s2, right? Principal quantum number 1, there's 2 s spinning electrons in that first row. Now I go down to principal quantum number 2, now I'm in the second row, I have to go through both of those s spinning electrons, so s2. Once I get to both of those s spinning electrons, I can go over to the p section, right? sp, now I'm in the p section. And I have to indicate I'm still in the second row, still on the second principal quantum number, but now I'm in the p spinning electrons, and oxygen is 1, 2, 3, 4 spots in that p section. So if I'm looking at the way this is set up, what it actually is kind of telling me in a shorthand way is if I look at oxygen, here's the nucleus of oxygen. Since oxygen's atomic number is 8, it's going to have 8 protons in its nucleus, right? Oxygen's in the second row on the periodic table. That means oxygen's going to have two rows or two layers, two shells or orbitals or energy levels of electrons. In that first energy level, I have two s-spinning electrons, right? One of those electrons is traveling in this direction. The other electron is traveling in the opposite direction, and they're spinning in a circular manner because they're both s-spinning electrons. In my second energy level, I have two s-spinning electrons, right? There's my s-spinning electrons. But now I'm going to use a different color here to show the p-spinning electrons. There's red for the p-spinning electrons. 1, 2, 3, 4 p-spinning electrons, and I can think of those p-spinning electrons as sort of spinning like this, right? They go out to that same distance, but now they're spinning in a different way that's not necessarily circular in nature, right? It's sort of this dumbbell shaped, and that's what I'm showing using this shorthand abbreviation. Let's keep going. Let's do something a little more complex. Let's go down, hop down to calcium. Look at where calcium is on the periodic table. Here's calcium in this slot. So we got to do everything all the way up to calcium. So we do the electron configuration. For the periodic table as well as. Alright, so here's calcium. We have to go through the 1s level, 1s2, right? The second one, second principal quantum number, s-spinning electrons, there's two of them in that second layer. Also in the second layer of calcium, there are those d-spinning electrons, so I have to show that that's the second principal quantum number, still the second energy level or orbital. D, and there's 1, 2, 3, 4, 5, 6 of those d-spinning electrons. Now I've got to go down to the third energy level, so I'm going to use 3. SP, oopsie, sorry. Checking to see if you guys were awake. Everybody was so quiet, I wasn't sure. Yes?
Do you not count helium?
For purposes of electron configuration, I like to count helium and hydrogen sometimes get swapped back and forth because they're so tiny elements and they're so light that sometimes they act more like metals, sometimes they act more like a non-metal. And the most electrons that helium can have is 2 in its outer shell, so it really isn't the same as a noble gas. So for purposes of electron configuration, I tend to think in my own mind of helium being right here. Okay? Yes?
How did you get the 2s?
Well, I'm not done. Let me finish, okay? Let me finish. So we're looking at calcium. We got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So there's the electron configuration for calcium. I'm going to go over it again. 1s2 is the first two elements in that first row. 2s2 are those two. 2p6 are these 6 here. 3s2 are those two. 3p6 are these 6 here. 4s2 are those two. And that leads us to calcium. You can double check your work by adding the exponents. 2 and 6 is 8, 9, 10, 16, 17, 18, 19, 20. 20 is the atomic number of calcium.
So, for the S value, like where it gives the 2 and the 6s,
2s where?
like, or just say, like, 1s2 and 2s2 and 2p6, like, to the exponent,
Right.
Like, the number of elements in that row.
Electrons. The exponent has to do with the number of electrons that are in that energy level or orbital that are spinning in that way.
So, like, but the 6 that corresponds with the vector, 6 elements in.
Well, it corresponds 2 ways. It corresponds that there are 6 of those p-spinning electrons in that orbital, but it also corresponds to there's a total number of 6 positions in the p section of the periodic table, right? There's a maximum number of positions or electrons that are in the s level is 2, right? Because I got 2 spots. The maximum number of electrons in a p sublevel is 6. 1, 2, 3, 4, 5, 6. What's the maximum number of electrons in a d
suborbital, 10, all right? And then F is 14. Let's continue on with electron configurations, and I think this will start to make more sense. More examples tend to help people see things a little bit better. All right, we're going to get to something a little more complex now. Let's try copper. So what copper is here on the table? Copper here is element number 27, right? So we're going to do copper. Got to do everything all the way leading up to copper, and I'm going to throw a caveat now dealing on this situation. So copper is here. I have to go through 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. I want you guys to catch up to that point, right? We've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, but now when we get to the D section, right, here's the D section, the D sublevel lags one behind in principal quantum number, which is this value we call n, right? So the D sublevel lags one behind in principal quantum number. So when I get to 4s2, I think I'm actually in 4D here, but it's not. It's 3D. So my next entry is 3D, and I have to go to where copper is. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't have my glasses on. I was looking at cobalt, I think. And actually copper is what I wanted to do. Alright, so let's add up and make sure I did the electrons right. 9 and 2 is 11. 6 more 17, 18, 19, 25, 26, 27, 28, 29. Copper is in fact element 29. You can also do a shortcut. Okay, you want to do a shortcut? Copper, you don't have to write the whole thing out. You simply say that the core electrons of copper look just like the noble gas directly preceding it on the periodic table. So if copper's here, what's the noble gas right in front of it? Argon. So we say, all right, copper looks just like argon. So I put it in square brackets, saying that the core electrons of copper look just like argon. Now I'm going to add everything past argon to get me to copper. So there's argon. So now I have to go down to 4s2, right? And then 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's the shorthand electron configuration for copper. Yes?
On our homework, it says that the formal configuration for copper is 4s1, 3 to 10, because it wants to fill the E orbital first.
There are some weird anomalous things that I'm not going to quiz you on the weird. There's like half a dozen elements that do weird anomalous things. I'm not going to pass it through those. Yes, just.
So we do the shortcut.
The last noble gas directly preceding. All right. So now let's think about ions. If I made a copper ion, which has a +2 charge, what does that mean about its electronic structure? What's happened to copper in order for it to become a copper ion with +2 charge? It lost 2 electrons. Where do those electrons get taken from? The valence shell. So, would I choose electrons that are there? No, I would not, because that is not the valence shell. What is the valence shell? The 4s electrons are the valence shell. So if copper is +2, then the electron configuration for copper +2 is 1s2, 2s2, 2p6, 3s2, 3p6. I lost both of those 4s2s as valence electrons, so I don't include them, and I simply say 3d9. So that's the electron configuration for copper as an ion, which is different than copper as an atom. You have to think about where it's losing its electrons from.
So why is the S is there valence electrons?
That number right there, what does that mean? This is 4.
Yeah.
What does that number mean about where those s electrons are? the furthest from the nucleus, right? They're in the fourth orbital, okay? Those are the third orbital electrons. We have to remove valence electrons from the fourth or valence shell. So that's why those are the ones that we lost.
So we want to say if we want like bromine or something is set to
Let's do a negative one. Let's do oxygen. I think we had oxygen before, didn't we? Yes, we did. Here's oxygen's electron configuration. All right. Oxygen, when it becomes an ion, it gains electrons, right? So where would it gain them? Where would I add electrons if I have oxygen minus 2? This would, no, not an S. What's the max number that can sit in an S electron orbital? 2. We can't put any more than it can hold, so where do the electrons gotta go? See how that works? There's also something called an isoelectric, or I've also heard isoelectronic series. You will have questions like this on the quiz on Monday and on the exam that you take over this unit. Everybody's ears are perked up, right? Isoelectric series. Here is an isoelectric series, and I'm going to ask you if, once you see the isoelectric series, you can define what this term means. Okay, here is an isoelectric series. Oxide ion, fluoride ion, neon atom, sodium ion, and magnesium ion are all isoelectric or isoelectronic with each other. What does that mean? They got the same number of electrons. They're wearing the same clothes, right? Does that mean if you borrow somebody's clothes that you're that person? No, definitely not. You're still the same person on the inside, right? You're just wearing the clothes of another person. That's exactly what's going on here. It doesn't mean the atom is changed into something else. It just means it has the same electron. Whose electron configuration are all of these? Whoops, I forgot this one, didn't I? Someone's going to tell me Jared, thank you. Whose clothes are all of these atoms wearing? Whose electron configuration do they all have? Neons. They all have neon's electron configuration, and they like that electron configuration. Why? Because they got a valence and an electron configuration of 8. Alright, so they all have 8 electrons. Who's the biggest and who's the smallest? You might say, well, wait a minute, they're all the same size, right? They're all got the same number of electrons, the shells and subshells, but that's not true. They're different size. There are definitely some that are bigger than others. What dictates how big it's going to be? Number of protons in the nucleus. How many protons does oxygen have in its nucleus? It has 8 protons. How many does fluorine have? 9. How many does neon have? 10. What about sodium? 11. Magnesium has 12. All right. So those protons, how do those protons feel about the electrons that they're all wearing? The protons like the electrons and want to be closer to them, or the protons not like the electrons and want to be far away? They like them. They opposites attract, right? That's what Paul Abdul told us, right? Opposites attract. So the protons in the nucleus are attracted to the same electrons. Who has what is the book will term the most effective? We have an ECT, effective nuclear charge. Who has the most effective nuclear charge? Magnesium has the most pull. It's got 12 pluses in its nucleus. So it's actually going to pull those electrons really tight. It's going to be the smallest of all. The biggest is going to be oxygen. Why is oxygen going to be the biggest? It has a whole lot less pull. A less effective nuclear charge. So that's one reason that ions and atoms change size, is this idea of the effective nuclear charge. There's also the idea of what's called the shielding effect. The shielding effect is when you have multiple layers of electrons between a positively charged nucleus, right, and the negative valence shell. So electrons in here versus electrons in here. Electrons here have zero shielding effect because there's nothing between them and the nucleus. This electron has one layer of negative charge and another layer of negative charge between it and the nucleus. So this electron has a higher shielding effect than this one or this one because these layers are negative and they shield the positively charged nucleus from that outer electron. So the further you get away from the nucleus of an atom, the less pull it has, not only because of the fact that, proximity, but also the shielding effect. Distance is both aspects. All right, any questions on electron configuration? I know this is a lot to absorb at once. Yes?
Which element has better shielding?
Probably the biggest one, like francium. One of the bigger ones, the electrons in the outside of francium have the biggest shielding effect because of the fact that they've got they got 6 layers in between francium and the nucleus.
So what you're saying is, even though magnesium has a higher effective nuclear charge, the shielding effect is negating some of that.
Well, no, in this case, the shielding effect is all the same for all of this particular isoelectric series because they all have 2 layers of electrons. So the shielding effect is not necessarily taken much into account in this situation, but shielding effect does take into account the electronegativity of an element decreases the bigger it is because the shielding effect shields the positively charged nucleus.
So the larger the elements, as far as the effective nuclear charge, the smaller the atom gets. But the larger the elements.
Wait a minute, let's back up on that one. The larger the effective nuclear charge, the tighter it pulls the electrons in.
Right. And that happens when you get more and more neutrons or protons in the nucleus.
Exactly.
So, well, with the shielding effect, so basically what I'm saying is the shielding effect kind of negates sort of what's happening with the nuclear charge. It's kind of more
A little bit. And that effect, this idea of the shielding effect relates to francium, or excuse me, fluoride, being the most electronegative of all the elements, meaning it has the highest electron affinity. Right, so you will hear both of those terms used interchangeably, electronegativity or electron affinity. It means that fluorine is doggone greedy for the electrons of other elements. Another element goes zipping by fluorine. Fluorine will pretty quickly grab electrons from almost anything, especially metal. But as you go down in this group, all the way down to like iodine, iodine is a lot less electronegative because the shielding effect is shielding the positively charged nucleus of iodine from being able to grab electrons like other elements. So electronegativity, we'll talk about this trend in chapter 7. The trend for electronegativity is in that direction as you go bottom to top and left to right due to this idea of the shielding effect. Alright, well that's what I got for today. Don't forget to come to lab.